Uh, are you audible? Online participants?
Yes,
Yes,
sir.
yes.
Yes, you.
Yes,
Okay,
sir.
thank you. Okay, good afternoon. So difficult session to handle, you know. I mean, especially those who are here after having a good food. Please, I don't feel like being here. Okay, I have to make sure my dinner is secured. So need to do this. Mm. So what plan is that? I mean, obviously. So how did it go your lab session in the morning? Just initial exploration, playing with the thing. So is it okay or how did it go? Okay, so plan here is that we'll keep the theory part very small. So effectively, though we have dedicated 1 hour, we'll try to finish in half an hour so that have longer break, come back for the hands-on session, which would be more handy. Okay, and let's see. So these are two components now. Right now, I'll be discussing the incompressible point volume part in OpenFOAM, followed by the hands-on session on the incompressible problems. And then tomorrow morning, I would discuss the compressible equations, followed by the hands-on session. And then you will have the two-phase system and the turbulence, which would be the hands-on in the tomorrow afternoon. Okay. So just to recap your memory since morning, what we have talked about the CFD different processes, pre-processing stage, and the post-processing stage. Pre-processing stage where you identify the geometry, essentially the problem definition, and do the grid and all these things. Processing stage where actual your computation you do, okay, and what you do here So what we are going to talk about is that, I mean, online participant, please, if you are not doing anything, just put your microphone in the mute mode. Otherwise, every time message or something pops up, this kind of noise will come. It will actually spoil the whole recording. Okay. Processing stage is something where we are now going to look at it, how the PDEs are implemented. Okay. And post processing is something that you need to visualize the data. Probably hands-on session, you would explore some of this thing. Okay. So now what is so if you see the problem definition, what you need you have the geometry, so you have to have the grid, and there are primarily two broader classification of the grids. One could be structured and another is the unstructured grid. Even in the structured grid, you can have the regular grid, which is typical Cartesian grid, X, Y, Z coordinate system, cylindrical grid, which is R, theta, Z, spherical grid. And these are this is an example of an Cartesian grid. This is typically polar coordinate. It looks like that. This is spherical grid. Then you can have curvilinear grid. These are, or you can have block structure. This is a block structure grid. You can have curvilinear grid. That means I have a curvature or complexity in the geometry. So I try to have a still generate and structure grid around that. Or you may have unstructured grid, which is again of some regular type or completely hybrid grid. Hybrid grid means I can have structured, unstructured kind of combination of that. And unstructured regular, you can have hexahedral, pyramid, tetrahedral, prism, all these different kind of elements are possible. Unstructured in a sense, it's totally unstructured. That means the grid's pattern could be different. So these are some of the variations that you can actually use to generate the grid around your geometry. Huh? So now how you are going to have the grid terminology defined for the solver. So the typically the finite volume you can have. So here we are looking at a simple structured kind of a Cartesian system. So one case you could have a staggered grid and one case you could have a collocated grid system. So what it does, staggered grid means collocated is a simple thing to understand. I have divided the geometry in regular cells like that, and all my flow variable which are solved, they are solved at the cell center. So that's a standard nomenclature of that. So I'm solving everything at the cell center. So when you talk about finite volume, there is a slight difference between finite difference here. Everything in terms of a particular cell we talk about, and the flow is solved around that particular cell, and everything is cell kind of stored. That means your flow variables u, v, pressure, and any other scalar, everything is stored at there. So that's typically collocated. If I go to staggered arrangement, it's just like you, if you look at this for a particular cell, you define the velocities at the faces. That means my U is going to be defined here and V is going to be defined here, and cell center I'm going to store it. So that means for U, I will have a separate, actually the shifted by half of the cell, you will have a separate cell volume, and for V, it's another cell volume which is half of that. So the thing is that any scalar like pressure, temperature, anything that you store in the cell center, for that typical this structure of the cell center you consider. For you, since you are defining at the faces like this, so you consider this as a volume, and for V it is defined here, so you consider this as a volume. So that means you need to maintain three different data structure. I will have a geometry. Once I get the cell numbering done, then for U and V, I have to shift it and maintain a different data structure for that, because that definition would require for stagger arrangement. Now, why you do that? This has some advantages in terms of some checkerboarding issues and things like that, which are typical problem in finite volume, especially in incompressible flow solver. Okay. So, and when you talk about a cell, three terminology which are important. One is cell center. We'll have the surrounding the cell center, all the surface which are called cell face, and the corners which are the vertex. So these three terminology, they are very, very important for defining a particular cell. So that will use it in the further slides. Now, when you talk about the solvers, there could be different situation, which are the physical situation in hand. You can have steady, unsteady. You could be laminar or turbulent. Laminar or turbulent, it depends on your particular flow condition. So viscous or inviscid, incompressible, compressible, single phase, multi-phase. I mean, then you could have reacting, non-reacting. And depending on that, how many conservation laws or the partial differential equation you need to solve, that would dictate by the standard governing equations. Continuity or momentum, energy, you require equation of state. If you are solving turbulence, you may need to solve the turbulent transport equations. If you are solving species mass transfer, then you need species transport equation. If you are solving two-phase system, you need to track the surface. So all this will add on to the list. Solution, how would I solve that equation? Obviously, I am doing those numerical approximations and assuming finally I get the set of system which I have to solve through the computer programming, then I can solve two different ways, either direct ways or iterative ways. This primarily mean to say that uh, it is little bit connected with your time discretion also of the whole system. Then the whole system, are you going to coupledly solve in implicit or explicit fashion? And then the linear part, how are you going to handle it? So since the actual problem size that you will be dealing with it is a large, the direct methods are not that very preferred. Most of the time we try to use the iterative based, because your linear solver is the one component which is going to consume more time in your computation. So now when we have been talking about the floating point operation, there again now we have a bifurcation. Which component of my program or the code is going to take time? Here the most of the time the metric system solution is the killer. So we have to reduce that thing as much as possible. Now, obviously, when you try to visualize the data, So you can kind of use different post-processing tools, which are some of them are freely available, some of them not. I think ParaView is freely available. Excel not freely available, but Sigma plot probably freely. RStudio is freely available. MATLAB is not. Origin Pro probably not. TechPlot is not. I'm sure. So you can use different, and there are others also. And why this is also important, because your output of the solver or the code has to be compatible, readable, compatible to all any of these visualization software that you use. It is not like that whatever I want to use, I can use it. It again depends what kind of solver you have, what is the IO you are using. I mean, the best possible thing, can somebody tell me what is the best thing? I mean, the thing that I can do, then I would not bother about what is the package I would use for visualization. That there is a one unique format that I can write and then anybody can read it. What is that format? ASCII format. So if I write in the ASCII format, then anything I can read anywhere. But that is not again recommended, especially when you do large scale problem solving. You know, because if you try to write ASCII, your data size is going to be huge. You think about a problem which you will solving, talking about millions, few million cells, few million cell with the number of variables you are solving. That is what you are going to write, and with different time steps and things like that. So if you write ASCII data, terabytes of terabytes data, you will be writing from one set of simulation, which may be junk. After a few months, you may get to know. So that is something one has to be again careful. What is the format you would like to write, so that. But there are some standard format like SGM5, CGNS. These formats are readable by most of the visualization packages. So format is another important aspect of large scale CFD solvers. I'm not talking about 100 lines, 200 lines code. I'm talking about large scale CFD solver where this is also an important factor. Now, let's look at the governing equation that you are solving. Again, going back to our old fashioned typical control volume approach, where here I'm not talking about what is phi. Phi could be anything. So over this control volume, the equations that you have, that's a change over phi over a particular time interval delta t. That is, I mean, this material volume. Then you will have the total surface fluxes and you will have the source term. Term one will have essentially the ddt of that volume integral of that variable phi, which I can write in two component. Probably one is the time derivative, another component the divergence of that, which you might know. So essentially this is the time derivative component and this is your convection term. Term two, I'll have the diffusion. So it's a surface integral, but from surface integral, I convert it to volume integral using divergence theorem. So basically you apply that operator, and then here also the diffusion depends on the equation. If it is momentum equation, diffusion would be your mass diffusion. If it is a mass transfer equation, there is a diffusion term, temperature equation, thermal diffusion. So, and accordingly the gamma, the diffusion coefficient, which is generic in nature, it can change. Third term could be source term. If you have source term, it would add to that. If not, then everything here, if you look at it, they are written in terms of the volume integral. And if you put them back, so then I can take out the volume integral to one side. So this is my overall governing equation. And once I integrate over the volume, that sums to 0. And finally, you get this equation. This is an equation which is true for any conservation law that you have. You can derive mass conservation, momentum conservation, energy conservation, everything. So ideally what I'm having here, one unsteady term. I am having a convection term, diffusion term. Depending on the equation, the diffusion coefficient would change. Essentially, this is a Laplacian term, this is a gradient term, and this is source term, and this is the time discretization term. So now if I have a 6-phase control volume like that, which is arbitrary in nature, so all the fluxes would act on the surface. Like if I take this room as the control volume, the whole thing would be the volume. Any source term sitting here, that would be volumetric source term, and anything passes by the walls or goes through the wall, those are the surface fluxes. Same thing here, along the surface you have the fluxes. I have all this equation, and this is what you do in OpenFOAM. The first term is my time integration term, ddt. Second term is my convection term, which is divergence term. Third integration term is my Laplacian term, but I take the negative, so I'm taking this, switching the side. Source term is the last term is the source term. These are the typical syntax of the OpenFOAM. So with that, I can actually derive any new equations or anything I have to program, I can program in the same syntax. So here, this is what one has to know. You have this interpolation operator. So what are the classes that is used? Explicit discretizations, you have this DDT, divergence, gradient terms, which is in terms of FBC. You have implicit discretization, then you have the FVM term. So there are type of database, there are class of the data structure in OpenFOAM. So that if you know, then this is writing this is kind of very easy. Now, end of the day, what you get a equation system like that. So that's a more simplified system. Over a cell, I will get an equation which is a linear system. Why I am saying that here W, N, S, C, and then I have the source term in the right hand side. Now I can have three different kind of boundary conditions. One could be Dirichlet boundary condition. That means when I'm defining the variable, I can have Neumann, that means gradient kind of condition, and I can have mixed. Just to give you an example, finally, even if you have three-dimensional, you kind of boils down to a, to just to understand this particular cell along this plane, I have the boundary which is specified. So that means I'm saying that at the face, the value which is specified. Then what I will do, all these east, see this suffix are for a particular cell. If I consider, then I will have it's, if I consider the two-dimensional cell, east is marked as a E, west is west, so it's a standard, and north is the north and the bottom is the south. So that's the standard typical convention that is. So now in this particular cell, if I look at it, the right hand side or the east face is given the boundary condition. So the east face coefficient you make the 0 and rest you modify accordingly. So that the boundary condition, if it is defined along the face, accordingly you change that, and then the AC coefficient you modify. So finally, the boundary condition has been implemented. Similarly, if I have a Neumann condition which is defined at that phase, so what I will write that the diffusion coefficient and the gradient term of that direction I want to take, and that is given. So QB is the gradient condition. It could be the any gradient which is, I mean, sometimes given a flux or sometimes 0. Then again that east coefficient is 0, and then rest you modify. And the beauty of the finite volume here is that the fluxes can be defined exactly, or the boundary condition if you have, that can be exactly brought into the system of equation, because you are having a conservative system across that particular cell, because I am writing the system based on all the surfaces where the fluxes are taken into consideration. So anything defined at the face which is to be, I mean, easy to implement in finite volume. Similarly, if I have a Neumann condition, same way right hand side I will modify, and rest of the coefficients I would. So when things are defined at the east face, the east coefficient are 0, and then rest of the coefficients are calculated and the AC is modified. If it is on the top north surface, then north would have been 0, rest would be taken care of accordingly. It could be at the west face. So any face, if I have a boundary condition, so I'll identify that face. and I will modify the coefficients and then implement it. So that the linear system that I'll get the matrix, automatically those are sitting, those coefficients, they are taken care of. Okay. So what you do, you have, I mean, if I come to the incompressible situation, I have the continuity equation. So I'm writing in terms of unsteady term, and I have the momentum equation. This is your Laplacian term, pressure gradient term. And so this is a purely a nonlinear equation. You have stress tensor, you have a velocity field defined, pressure field there. So I have to have an ways to solve it. And typically what you do in the incompressible case, you break down the system in two parts and then try to solve it. Now, again, what you try to look at it is the momentum equation discretization. Here, this is my momentum equation in, I'm just writing one dimensional system. So this is the stencil you can think about. So you have a particular cell. For C, you are writing the equation. Behind that, the west cell, right hand side, the cell is given as the east cell, and this face, this would be east face, this face would be the west face. And since it's a one dimensional, I don't bother about the north and south, but if it goes to two dimensional, you take the north and south as well. This would be little easier to comprehend. So this is my one dimensional system having the pressure gradient and the term. I will write the volumetric integral here. And this is what, using the divergence theorem, you get it. Similarly, you have the continuity equation and write that complete cell, you integrate over that and get this. So finally, what I do, this particular one, I'll try to discretize it. So what I'll try to discretize, this is over the, this guy is over the faces. So since it's a one dimensional stencil, I have east face and west face. So this brings down the rho u, delta u, and ue, and this is in the west face. So you take the direction because it's a surface integral. And then you have this component, which is mu del u del x del y in the east to west. So I am doing the integration between this to that. And this is the pressure gradient term between that. If you see, this guy is essentially from continuity, I get this over the surface. This is the mass conservation equation. So here, this you replace with the mass which is passing through this phase, and this the mass which is going out the west phase. So that if you put it, then finally this equation becomes the, this is your m dot ue, m dot w, I mean west phase uw, and then the stress diffusion term and the pressure gradient term. So finally, that if I put it in terms of matrix, it will look like that. And I have the complete mass conservation equation. Okay. Now from here, what I'll try to do is that I use these two equations to solve my incompressible system. And how you do that? You try to, the way the algorithm works is that these are pressure based systems. So we call it a pressure based system. Since it's an incompressible, we try to decouple the pressure and velocity because that's the connectivity between this. So we try to decouple. How you decouple? You say that, I mean, okay. So what you do here, since this pressure gradient is there, so if I don't have the pressure gradient, rest is in terms of velocity. So which is easy to solve. So let's assume the algorithm in a global sense, it works in a fashion. I decouple the pressure. When I say the decoupling the pressure, let's assume pressure field you ignore. You start solving the velocity field with some guess, initial guess. It's an iterative process. Once you get the velocity field from this equation, you solve it. From this equation, you solve the velocity field. Now, actually, I have in reality pressure gradient, but now I have, for simplification, I have taken out the pressure field. So I would get some velocity field after solution. Now the question here is that what I get the velocity field, do you think that's the correct velocity field? Obviously not. So I have to correct it because the velocity field which I have got, I have not considered the pressure into it. So while you correct it, that you put back that in the continuity equation and get the corrections for that thing, because the velocity field that I have opted, you think about it's the intermediate solution, which is not the correct one. And it's not going to, ideally, I should have. So I
Sir, we are not able to hear. Hello? Sir, we are not able to hear you.
you viewed them. So you get the corrections equation there, and then so the correction equation, then you solve, use that updated system, resolve your velocity, go back. So that is why it's called the, this anyway we have talked about it. So this is why it is called the pressure based system, where you decouple the velocity and pressure, solve separately. Now straightway if you come to the icofoam solver, how? So this is the equation that I am solving. I have a, I'm just only showing you the term, which is, this is the unsteady U equation, convection term. This is my diffusion term and the pressure gradient term. And this equation I am discretizing with the time discretization, straightforward. And from discretization of the convective and diffusion term, I will get this, and I'll have the pressure gradient term. Okay, both convection and diffusion, I have got to this system. And then this equation I can recast into this particular form, basically rearrangement of this particular equation here. Still I am having the pressure gradient term. And the way you finally get the matrix equation, AP into UP, this contains the off diagonal terms and the half of the transient term and the pressure gradient term. So this is the final equation you get in OpenFOAM, and this is the diagonal coefficient terms with the velocity gradient. Then this equation I solve, okay, UP I will solve the whole thing divided by AP, and so basically these coefficients I am, but this AP is not a scalar. AP is sort of an matrix, what I am getting. So when I'm dividing that, that means I have to do the calculation there. Now, if you combine this equation with the continuity equation, this UP, what you are getting, assume that's the intermediate solution. Then if you put it back in continuity to satisfy your mass conservation, which is having this pressure gradient, so finally you get an equation in terms of the pressure Poisson equation, which is going to correct your mass because of decoupling. Okay. So what you have then, total equation, if you see that you are solving del dot U0. You have the X momentum equation in this fashion. You have Y momentum and V momentum. So typical piezo system, the way you start the time loop, this is what you exactly .c file, if you try to see there, you start the time loop Okay. And then you calculate your stability criteria. So you need to, since it's a transient calculation, you need to establish your delta T or calculate your delta T based on the CFL that you have defined. So satisfying that from this subroutine will do that calculation and define your delta T. Then here you find out the momentum equation matrix. And I am writing ddt of u. You see this term, divergence of the u, this term, Laplacian term of u, this term. I am not done the pressure term here. Then I am doing the correction equations of that. That means now I'm solving a u equations which will be equal to the gradient of the pressure. Exactly, this is the equation, Laplacian equation for the pressure, where you have the velocity there. So that's the equation you solve and you correct your velocity and then go back into the loop. So it goes in a iterative process. This you do, and the beauty is the OpenFOAM is that if you write in this fashion, it will take care of all the dimension. You don't have to write, okay, x direction, y direction, because u itself is a vector here. Okay, it takes care of that because these are all defined at the data structure level. But this, if you do, it will do that. Now, if I go more details. So here in the corrector loop, this is where I stopped the piezo corrector loop. So now I'll corrector loop if I look at it. So this is here you update the AP and freshly you compute. So these terms are all the unsteady blue circle terms are the unsteady calculation that each and every line. So the metric system that we have got here, here and here, that you calculate here in the PJ correction loop. Effectively, you calculate the AP and U, AP by H, then you do a boundary conditions update, then you have these pressure corrections. So the that you do, and then you add the term here, whatever the rest of the term is there. Finally, you update the velocity and then go back. So this whole code, first you solve u without the pressure, then you go to the pressure corrections. Once you do the pressure correction, then you update your velocity again and go back. So this goes in a loop. So I have decoupled, that's what it's typically called the pressure based solution methodology or pressure based solver, where I have decoupled the pressure from velocity, but then I take into account through my mass conservation. So I'm not violating none of my basic governing laws. So continuity I have to satisfy, momentum I have to satisfy, but I do in more steps. First, I assume there is no pressure, solve it, which is intermediate. It is not going to satisfy my mass because mass conservation has to be there. Whatever error is there, that's my correction for pressure. I solve the pressure. Using that pressure, I update the velocity, solve the velocity, update it, go back. So that I make sure within a iteration, my mass conservation is satisfied. Because if you don't do that, it starts accumulating that error and it will propagate with the solution. So your solution is going to be contaminated. Okay. Now, what you are going to, these are the scheme to solve this term. So this is the time discretization term in the system. So I can use, these are the available thing that DDT if I write. Now DDT I have to define. So this is you define in your system FB scheme in your case setup. I will come to that also. You define your DDT scheme. If you don't define, OpenFOAM would solve the problem. And it will take the Euler. Euler is essentially first order accurate. That means if I have to do del U by del T, it will take UN plus 1 minus UN by delta T, period. So that's what called default. Now I can write anything I want to update. So here I can do second order, I can do Crank-Nicholson, I can do anything, I will update here. Same way gradient scheme. Gradient scheme is the this pressure gradient term. So there is a default which is Gauss linear second order. But I can define for individual component. Then my black one is the divergence scheme. Default there is none. Then velocity you can give Gauss linear, which is again second order. You can define others. Bunch of these divergence schemes are available there. And the if you want to find out something, you can go to the web-based things. You can find out. If you don't want to find out, you put something here. I don't say Gauss linear. You put X, Y, Z, anything. you try to run the solver. It will stop there and give you the options available. So even if you don't know what are available options, any of these schemes you can find out what are the available options. Provided you don't by default put this keyword, you put anything else, it will just give you the option. Then you can accordingly correct that. And the Laplacian term, the green one, you have Gauss linear, which is again second order. So these are the things goes in your case setup. I mean, this again morning we have showed that your case setup will have zero conditions where you give the initial conditions, pressure, velocity. So these are, that means when I'm solving pressure, I mean flow equations, I need to define pressure and velocity. So that's the basic thing that you have to do. Then you have the information that is required in terms of your grid in polymesh folder and the transport properties. If I'm solving only momentum, then viscosity. If you are solving it in non-dimensional form, you can give in terms of Reynolds number. Then the system which is having the control dict, FB scheme and FB solution. FB Hello. So we can, so that's your directive structure typically that you have. So here is again in terms of icoform control dict. Let us look at it, what we can control. You can see the application you have to provide. Yeah, this they cannot see, right? Okay, I'll do it. Okay. Okay, so uh, uh, so here, if you look at the control dict file, what we give the control. So one is that application that you in the first line, you see that icoform, that's the solver that you actually provide. So you can provide a different solver, whatever you want. This is the solver name. It could be pimple, piezo, depends on multi-phase. Then you give start time. What is the time you want to start? I mean, initial time, whether it's 0 or I had a previous time step, I'm restarting from a particular interval, then I can do that. Then your end time also you provide. Then what is the final time that you want your simulation to run? So up to 5 millisecond, 0.5 seconds, something like that. Your delta t that you provide. Your write control, that's the time step. Write interval, that means so many iterations after that I will write my data. Then first write, that means whether I want it or not. Write format ASCII. Then write precision, that how many digit after decibel. Then compression, obviously it was kept off. You can try out those things. Type format general, time precision, and all these are the control that you keep. So which is a fairly simple, straightforward. That what are my basic control. Then I come to the FB solution scheme. Now I have a solver here. First pressure, you see the linear solver. This is precondition conjugate gradient. PCG is precondition. So there you can play around again. There are multiple of them. What are available and all these, you can again put a in front of PCG, you put XYZ, anything, hit the button, it will give you the options, what you can possibly use for pressure. Then preconditioner is a direct IC. You use a smooth solver, then use systematic Gauss seidel. Then you provide also the tolerance limit that between the calculation of the errors. Piezo, you do how many intermediate corrections you do. So number of corrections you can increase. Orthogonality corrections, whether you want, because 0 or 1, it's a binary. Then you have the reference self there, you don't need to put anything. So that is more like an piezo algorithm control if you are using piezo. Okay. Now these are the two problem set that we are going to do in the hands-on. One is the typical lead driven flow where the upper plate is moving with a velocity, and this is the moving cylinder. So that means the mesh is moving with the cylinder. So there are two different kind of problem. Here you can run steady, unsteady, depends on the Reynolds number that you have. Probably we will do the laminar one, but if you go to turbulent or something, you have to go to unsteady solver. So probably EcoFOAM will not work. You need to do pimple or piezo. Here we will be using moving mesh, unsteady, so we will be using pimple. Some of the OpenFOAM things which I mean just like these are the some of the work we have been doing. So kind of applications you can see where a lot of mesh moving is there, the vortex structures. Then this is again instability over cylinder. So these are slightly heavy calculations. This is again how the mesh motion is taken care of, where the cylinder is oscillating. This is coupled with both flexible finite element solver with the OpenFOAM, where you try to do things. So here it is again a completely turbulent flows, which is Reynolds number is quite high, around 10,000. We try to do hybrid Rans LES calculations. The flow goes through, but a lot of periodicity in. So here you can see the tubercles. You try to improve the drag and all these things. These are all done in OpenFOAM different. So here the number of cells you see, probably the highest one that was run in the 18 million. So typical run times would be 3 to 4 months time. 3 to 4 months time. So kind of so the scaling, again, this is little bit of old data. It was done when this NSM, the machine that you have seen the downstairs, this NSM thing came up. Before that, we were doing this scaling for the vendors. So that time we did some scaling with the OpenFOAM. It was again, so there are two scalings. You see the executance time, and we have. So when you do scaling of a solver, there are two components. One is weak scaling, one is the strong scaling. So you see that typically large number of processors, the grid size has to go up. Otherwise, you don't get linear scaling. But that's not all, because here, if you see, even for a 100 million job, when you go to 1280 processor, you never. Ideally, if I increase the processor, it should go linearly, but that never happens. Now you start losing in communications, things like that. So you start seeing that effect. It's a very recent. That's what I mentioned the version. Now the GPU computing and all these things under the ExaProm project, there is a lead driven cavity problem. You can also go and seek that. So there are three different grid size taken: 1 million, 8 million, 64 million. And these are the sum of the setup. The idea is that you keep the setup similar so that you can compare things, how it scales. Okay. And what it was trying to look at different linear solvers. So what is readily available in OpenFOAM? So like foam, DIC, PCG, Okay, diagonally. Then you use the AMG PCG conjugate gradient with the uh, algebraic multigrid. See, the PET-C is another environment which is again openly available, and then there is a plenty of linear solvers which applied mathematics people use it. So idea here is that you try to use whatever readily available and try to couple with the PET-C also, try to compare how it scales. So these are the setup which was used. And obviously solvers is based on the velocity preconditioner and all these things. So you have four different configuration: home DIC-PCG, home GMC-PCG, PET-C-IC-GC, conjugate gradient, AMG algebraic multigrid GC. So it's a diagonal based incomplete Cholesky, DIC, geometric algebraic multigrid, GMC, incomplete Cholesky, classical algebraic multigrid, and the solver is CG, conjugate gradient, conjugate gradient, conjugate gradient, conjugate gradient. So this is the same setup used for everybody. So the iterative method you can have in two different convergence criteria. One could be fixed iterative criteria, that is okay, I'll do after few iterations every time step. Or you can have the fixed norms, like I would say this is the error tolerance I have to reach in every iteration. So either of that you can set it up. Or two different options which you can choose for the files where the I mean that you can do in the system and FB solution scheme, either the fixed iteration or fixed norm. So this is again in the FB solution scheme, you as a user can give it. And this is the situation of the scaling. You see that when I increase the, I mean, I have not done it, increase the number of processor around 4,000, something like that, the scaling is slowly dripping down. Even I have 64 million. So it could be multiple reasons. One reason could be the problem size is not good enough for pushing that job in so many processor. Second possibility could be my linear solvers are not effectively operating or effectively scaled over the number of processors. Third possibility is the effect of both. So that is what is the low number of processor, you see the scaling of the even the piezo foam itself is, and piezo PET-C both are similar. So PET-C and piezo OpenFOAM inbuilt linear solvers, they are kind of behaving similar way, but it depends on the problem size. When I'm pushing it to the large number of processor, probably not sufficient enough. So these are the issues one has to kind of know before firing a large scale job in large number of processor. I mean, I cannot do whatever I want. I may have abundant resources available, but not necessarily I have to use it. Use the resource also judicially. For that, again, you need to understand that system. Okay. So with that, we'll stop the theoretical discussion so that once you go back to the hands-on session, solve those two problems, and then extract out the data and visualize it, so that at least that completes the process for a one simple thing. If you have any questions, anything, that I would be happy to answer. Online, you can see anything is there. No, your question is that there are tutorials where inbuilt setup is there. If you run that, it works. Now you try to modify that for your problem. Now, I mean, it depends exactly what tutorial you have run or what setup you have looked at and what problem you are trying to modify. So whether there is a resemblance or the mapping is there or not at all. If you can be a little bit more specific, then know which value you are referring to. flow. Yeah.
Hello.
Yeah.
Uh, I can see that in control dict the start time is 0. So
Yeah.
how I can change the time, like, or how can I end the time like little more?
Yeah. It's just like, let's say I have run the job for 2 milliseconds. I have stopped it. So last time iteration data would be there in the directory. So that time, if I again start time make it 0, it will again start from the initial condition, which is the 0 condition. That means the previous data, it has overwritten or it will be lost. It's just like I have a, let's say, channel flow. Flow has developed this much. Next restart, it's a restart. I have to start that flow which has developed. Otherwise, what will happen? Again, start from the initial condition. So that time you have to look at the last file you have written, which is the right interval. The last time step you have written, that you have to put it here. Otherwise, it will again, the solver will start from 0. So that means again you will go that far. Because let's say you have an, if you are putting in HPC, you have a certain time, 2 days, 3 days, then to the 3 days, you will get certain run. You will get certain time step to run. Then you will lose out that time. So that start time will, okay, flow will start developing from there to again further. You go up to this, you have a right data. Third time you have to change that start time so that those data is stored. It's not going to be overwritten. So now if I want to see from 0 condition how the flow is developing over that pipe, I would be able to see that. Every time it is 0 means it will go from here to here, here to here. You will never get to come here. So that's where you change the start time. So the last time step you have, you start from there, use that as the initial state, move from there. Come here, use that as the initial state, move there. So that your flow develops completely. And you can see the overall evolution of the process. That's why that is going to be very, very important. So start time 0 means I'm going to start from initial condition based on my initial condition. So when you do restart this, this folder of 0 folder will have no influence on the solution. It is rather in the other time step which is written under that 0 folder, they would become important because that is from where it's going to start. So your start time in this text file is going to dictate, or you are asking the program or computer which file to look at it. What is my last state of the flow? Okay. Yeah.
So first question is how to choose between GAMG and DCG solve.
Yeah. So the question is that how you choose between the PCG and
Please.
DIC. Yeah, these are the things actually, unless you have a fairly good knowledge about linear solvers, because there is a book on linear system solution or iterative methods by Yusuf Saad. If somebody is interested, look at it. So it's a complete book on only different linear solver. It is little bit mathematically involved, that how the every vectors in the linear system works. So these are connected with the norms, error, eigenvalues, spectral radius of the system, that dictates the solver their convergence criteria. So I want a solver which would be quickly convergent. The convergence depends on my typical matrix what I have, which is ideally a sparse matrix. So it's going to make my vectors are not all linearly independent. So I could have a very, very bad eigenvalues. My spectral radius could be high. So it makes me the linear system not to converge so quickly. Basically, it's SIP system. So you need to have a fairly good amount of knowledge to choose this. Keeping the understanding or the story short, I mean the PCG, DIC, these are the default one which are there. That pretty much works fine for by and large most of the problems.
Sir,
Yeah.
sir, can you repeat the book's name clearly, sir?
Yusuf Shad by Iterative Solvers. The book name is Iterative Solvers by Yusuf Shad.
Thank you, sir.
S-A-A-D. Surname is S-A-A-D. Okay. Complete book on linear systems.
question is, for multi-phase and 6 degree of freedom moving mesh problems, which solver is suitable?
So multi-body 6 degrees of freedom. There are probably 6 DF solver which is there under the development version. You may try to use that. OpenFOAM latest version claim that they have a more updated version which works well, but I'm not sure which would work because the one which I have showed you, we have our own spring mass damper system implemented. So we don't use the default one which is available. So you have to check it out which one works because freely available software, so not necessarily everything will work smoothly.
So next question is, can we get Reynolds number directly through simulations or should we calculate using velocity?
It's essentially a parameter which will dictate your flow pattern. So you know a priori what is going to be the Reynolds number. Local Reynolds number definitely you can obtain from your simulation, but the global one you have to define. Otherwise, you cannot select your models.
Is it possible to model FSI simulations?
Model to?
Model FSI simulations.
Yes, it is possible to model FSI simulation. I mean, rigid body FSI. This is what is one of that kind where you are going to do that. Whether the body is moving, the body is not getting distorted, but I have showed you an example where the body is getting distorted. This one here you have to couple the finite element, or you have to solve the solid mechanics equations within the OpenFOAM framework, which is also possible. They have a solid dynamic system. You can solve it.
Then can we use like user input formulas to calculate or monitor parameters? If so, how can we do it?
What parameter? Okay, I mean, you can do that. I mean, the control dict file, you can add on some more things. For example, let's say this problem in, I mean, Snehan, can you show the pointer also there? So let's say any of these positions in the domain, I want to probe the pressure, velocity, how it is changing with time. I can have the probe points, and those you have to define in the control dict file only. So there are control dict file, you have to do all the control of the whole simulation. You can write that out.
Is it possible to do hypersonic simulations?
Answer to that is yes. I mean, I think you can pose this question to the TA Anurag, who is the hypersonic man, who is. I mean, we'll show you some of the compressible tomorrow on the hands-on. Okay, but yes, it is possible, absolutely possible. Okay, so we'll break for half an hour. Sorry, 15 minutes, then we'll start the hands-on. Okay, so online participant join back by 4:15.
Okay, welcome back everyone. I hope you are now well aware of how to handle the Linux commands. First thing is I want you all to install ParaView if you have not already done, because without which I think we will be not able to move further. And apart from that, I have already created several folders named as NSM KGP named folder, which was earlier missing in all the test accounts, and it is available everywhere. Now you just have to copy all the contents of NSM KGP into your respective folders. Please don't edit inside that folder. That is the master folder, because if anybody messes up somewhere and if he wants to again restart it from there, it would be easier for him to again copy back all those original files. So if not, I will again quickly demonstrate how to copy all the contents of NSM KGP back into your respective folders. And from there onwards, you can start working for the first problem, that is lid-driven cavity problem. Okay. So shall I start again with whole process of logging in again, or are you okay with it? Have you has
Sir,
everyone
Has
logged in?
everybody logged it into their
Sir, in
accounts?
which directory there is
I
NSM
hope there is
folder?
no more doubts regarding login in. So in the first session, we were able to copy the files for test user 1. For all the rest of the test users, you will be seeing a NSM KGP folder. Even if you have copied from other folders, please copy from NSM KGP. Okay. So
So the command for that is write cp -r.
Sir, where
NSM
is
KGP,
NSM folder? In which directory?
and copy all the contents to my folder name in your respective folder names. If you have not already made, please make your folder
yeah,
name.
please make this, and those who have made the directories in home, so change your destination path accordingly. Okay.
Sir,
So all
where
you
is
need to do
NSM
is after
folder
typing this
located?
command, hit enter. It will take a while. And hopefully everything, all the contents inside NSM KGP will be copied into your respective folders in which you are going to work now. Okay. So please change the directory to your respective folder names if you have already copied.
Test user 1, everybody has copied the folders. Test user 2, anyone?
Sir, where is NSM folder located? In which directory?
ऑनलाइन यूजर जो बोल रहे हैं वो प्रेजेंटर सुन नहीं पा रहे हैं, आप लोग काइंडली चैट बॉक्स का यूज करें.
From your WSL subsystem. So if so, then what you can do is I have already shared that Google Drive link. There is one tar file. You can NSM workshop NSM KGP tar file. You can pick that and copy paste in your in that WSL, and then extract and start working from there. It would be much more convenient in how the way I would be basically demonstrating how to use that. Or if you know the lid driven cavity problem from where to adapt, you can directly copy paste from the IcoFOAM tutorials. Okay, so today is day 1. So I'm basically going inside OpenFOAM day 1, and you can see there is one folder named as incompressible. Of course, today we are going to just deal with the incompressible flows. And if you go inside that incompressible flow, this is my present working directory. You must follow this.
Okay, so everyone, the file is in Scratch. Okay, so those who are not able to. So Scratch is cd and backslash Scratch backslash.
If you want to go to Scratch, use this.
Just so so for going, so your files will be in Scratch. So going to Scratch, this is the command cd dollar $scratch. Inside this NSM KGP is there. Copy the folder, the command Anurag showed. Okay.
Once again, I will
Just show it.
show them.
The files are in Scratch. cd underscore cd dollar $scratch to go to the Scratch location.
This is the command for copying. If you have not already done, please do it.
Test user 1, everybody has copied. Anyone not copied from test user 1? Test user 2? Please raise your hands. Then if if everybody has done, we can proceed to the next steps then.
Test user 3.
Okay, here everybody has copied the files. Anyone left here, this side? No one. Here? Scratch is in caps, all caps.
So if you have already copied, please go into your
Please
respective
check
test.
your Scratch spellings, okay? Anyone from here still facing the issue in copying files? Okay, then I think we can proceed. Only one or two are.
Okay. So what I will be doing is inside OpenFOAM day 1 and inside incompressible, please follow this. This is my present working directory. You must change the directory to this particular location. Okay, the first problem is the lid driven cavity problem. Right. So I'll explain you physically what it essentially is. Basically, we have a cavity. We have a square cavity whose dimensions are whose dimensions are 1 by 1. Let's say meters. Sorry, 0.1 by 0.1 meters. Okay. And these are the fixed walls. And this top wall is attached to a conveyor belt, which is moving with 1 meter per second. So essentially, due to this motion, the fluid that is sticking over here will also travel along with it because of the no slip boundary condition, and flow will basically recirculate inside this. This is what we are going to simulate, and there are standard data sets available. Like if you make a line plot along this line and plot u versus y, that is y axis over here and u over here, you will get certain distribution. So basically that distribution has been already published in a lot of literatures. One of the literature is Ghia et al. So we are going to, I have already provided the Ghia et al. Data in the XML, in the Excel format. We are going to simulate the problem, extract the data along this line, and then try to match our results on top of this. And this is the part that we call this as a validation study. And after validation study, there are grid independent study. So initially, this whole domain is discretized into 21 number of cells in the x direction and 21 in the y direction and 21 in the x direction. That U will basically start to collapse on each other. That means how much you refine beyond that point doesn't matter because U is essentially going to be same every time. So at that point of time, we say that we have attained grid independent solution. How much you refine it further, it doesn't matter to us. And that is the optimal grid size that we need to use in a simulation to save the computational resources as well. So first thing first, we will first try to validate our results with the Ghia et al. Results. So okay, for the online participants, I will be again reiterating that. So for now, please follow the steps from here onwards. So basically, I am in the cavity RE100 flow. So a standard test case setup contains zero, constant, and a system. These are the separate folders that I've already provided to for the validation purpose. So inside zero, if you go, you will see pressure and velocity, right? So this is the zero folder that we need to give the initial condition as well as the boundary condition for the simulation because this is the boundary value and initial value problem. So if you look inside pressure, this is what the moving wall is. The top wall is the moving wall and rest of the wall, these three-sided are the fixed walls. So since we don't want the flow to cross the particular boundary, we don't want the pressure gradient in that direction, in those direction, we have imposed zero gradients on all the walls. Zero gradients means if we search or if we calculate the gradient, let's say in this point, which is outside the domain, if you have done basic CFD, we need a ghost cell for calculating the boundary condition. And inside this domain, at this particular location, if you calculate the difference, that difference would be zero. That is del P by del X would be zero. Similarly, in this direction, del P by del Y would be zero. So for all the walls, I am specifying that pressure is zero gradient with respect to pressure. And there is another patch. By default, OpenFOAM, what OpenFOAM does is it basically, we are solving a two-dimensional flow. The flow is varying just in X and Y. What OpenFOAM does is it tries to, since this is a generic solver, it tries to extrude that mesh in the Z direction. And whatever discretization we apply, same is applied, but only thing is it is just one cell thick. There is no discretization in the Z direction. If you want to put, then you have to put the boundary condition. So this is the front face. So this one, the portion which I am hatching is the front face. And similarly, there is a face at the back, right? If you are able to visualize, that is the back face. So both together over here is what we call as front and back. And since we don't want to solve in that Z direction, those boundary conditions are kept as empty. So OpenFOAM will essentially know that I don't need to solve in that direction. Similarly, if you look for U velocity component, U velocity boundary conditions, inside the domain, this is internal field, what it is showing. First of all, it is dimensions. Let me tell you, this is dimensions of velocity meter by second. This is M, L, T, and so on, the standard dimensions that we have available. And this is the internal field. That means in the domain, inside the discretized domain, in each cell, it will keep value as 0, right? So for initial condition, we need some guess values, and that guess value is being provided by that internal field. Similarly, for boundary field, again, I said that is the top wall is moving with respect to in the X direction with 1 meter per second, positive 1 meter per second. And if you put -1, since this is a vector, it will go in the other way around, right? So, and other walls is a very standard case. It is no slip. Values, no slip will say that all the particles that is vicinity to the wall will stick to the boundary. It will not basically move along with it. And with 1 meter per second, the top wall only will move and particles will also move along with that at 1 meter per second. So this is the standard boundary condition and internal, the initial condition that is required to simulate this lid-driven cavity problem. Similarly, if you move into constant, there is nothing for now, but one important field is transport properties. So essentially, a lot of questions popped up while sir was discussing about the Reynolds number. So a priori, you must know what Reynolds number problem you are trying to solve. In Ghia's paper, he has solved Reynolds number 100, Reynolds number 400, and so on. There are a lot of data available. So we need to set the case set up according to the Reynolds number. So for this particular physical problem, Reynolds number is defined as U of lid into length of lid divided by nu, or rho VL by mu, right? So this essentially becomes the kinematic viscosity. So this is exactly what we have to feed in over there. This kinematic viscosity is 0.001, right? What we are trying to do is we are trying to simulate the Reynolds number 100 problem. As I've already said, it's okay. As I've already said, U lid is 1 meter per second, right? In the boundary condition, I've already specified this as 1 meter per second. And this length is 0.1. So if I want to keep Reynolds number as 100, you can do the back calculation and find out nu. It will exactly come as what I specified over here, right? Let's say if I want to put Reynolds number 400, then it is, I will leave it to you how you do it. And I'll ask you to, for your practice to simulate Reynolds number 400 and validate. I'll first demonstrate 100 case, then it's up to you how you do that Reynolds number 400. Or alternatively, what you can do is you can change the you can keep this kinematic viscosity constant. This is L lead as 0.1, and then alternatively you can play with u velocity, right? And then set accordingly a Reynolds number 100. So all this combination, what I'm trying to say is should give Reynolds number 100. So I prefer to play with nu rather than all these values, right? Sorry. That is again dimensions of nu. What is the units of nu? You calculate it, convert it into mass, length, and time, MLT. So whatever numbers it will get, m to the power 0, it will be L square. Dimensions of nu is meter square per second, right? So meter square will go into L square, and per second time will go to -1, t -1. So it is basically m0, L square, and t -1. So that's why 0, 2, and -1. And rest of the dimensions are candela, intensity, and all those things, which I'm also very much not familiar. Let me admit that. But only dimension that I'm now considered is MLT, and rest of the things you can keep as 0. So this was all about constant. Now, if you move to system, there are 4 important folders or 4 important files that you need to use. The first one is block mesh dict command or block mesh dict file. So you can use this particular file to set up your domain and to discretize the domain to, basically this is the meshing process. But thing is, here is no GUI. It is very hard to visualize. But I'll give a brief idea how this meshing process is applied over here. So first of all, the name as it suggests, it is vertices. First, I'm declaring the list of vertices for that domain. As I said, OpenFOAM needs that 3-dimensional domain. So there would be in total 8 vertices over here, right? So if you plot those vertices, right? If you plot those vertices, this is basically 0, 0, 0, right? So this is 0th point in OpenFOAM and all the standard language, programming language, every index starts from 0. Then again, other point would be 1, 0, 0. This is the first point, right? This would be 1, 1. This is second point. This is third point. So first 4 vertices are covered. That is, it is defining the back portion of the lid driven cavity. Other is again, it is asking like it is 0.1 in the z direction. So that plane is fixed. So essentially it is 0.1 meters. You have to come 0.1 meters forward from the coordinate direction. And again, the nomenclature would be 4th position if you plot those points, 5th point, 6th point, and 7th point, right? This is essentially declaring all the vertex over here. Other entry that over here is the blocks. So basically, after creating the geometry for structured meshing, you have to create a block over which you will apply the discretization, right? So this is a single whole block that you can use. This is a whole cube that is itself a block for this geometry. If you want to, I'll come that to later. If you have multiple, let's say very complex geometry, you need to break that geometry into several Cartesian blocks and accordingly discretize with number of points. That's why I'm saying that if geometry gets very complicated, it is very difficult to visualize which vertex will form the block. And accordingly, you have to match these grid points as well, the matching faces of the blocks, right? If you specify 20 in one and 30 in other, those blocks will not match. So what it is saying is use 20 grid points in the x direction and another 20 grid points in y direction. So essentially it is 20 by 20 cross problem. And there is just one. So what it is saying is whatever is the length of that, don't discretize it. Just keep, or to be put in other way, it is not the number of points, it is number of cells that you need to form. Small number of cells. This is the number. This is first cell, this is second cell, and there are 20 cells. And it is asking to put one cell only in the Z direction. First, only one cell thick problem that we are trying to solve. Now, this edges is kept as empty. This is again an advanced option for declaring the edges if you want to simulate a flow over cylinder, right? So you need to, if you have done OGrid sometime in ICM, CFD, or any other software, so you need to specify this as edge or curves. Again, this would be another curve. So things will get quite messy in block mesh dict file if you want to even solve a flow over cylinder, right? So for now, this thing is not required. So I've kept that as empty. Now this top wall should be moving wall. So whatever name you specify, whatever name, like if you specify my name Anurag, and then you type as wall and whatever it is there, and if you fire the block mesh dict command, so whatever name you have specified, that name should appear inside the zero and constant zero folder that I was talking about for the boundary conditions, right? So type wall, this is the first top wall that we need to define, right? That is moving with 1 meter per second in this direction. So that particular face is comprising of 3762 number of vertices. So that set is complete. One of the faces done, right? Other fixed walls that I was talking about on which zero no slip condition is to be applied are 0473, this face, right? 2651, this face, and 1540. So what we are doing is we are combining these three faces and naming them as moving fixed walls, right? You can type separate names, fixed wall 1, fixed wall 2, fixed wall 3, if you want to separate out all these particular entries. Similarly, we have to accommodate or we need to adjust our zero and zero folder accordingly for applying the boundary conditions. What it is saying is it is moving wall. So it is type wall. It can be patch also. It can be symmetry also. If you want, there are certain boundary conditions available, standard boundary conditions available. If you make that as type as wall, then you can apply the wall functions for k omega, k epsilon, and all those things. If you keep a generic type patch, it will say essentially it will fail. You cannot apply k epsilon, k omega. Wall is basically is used to handle the wall functions that we need to apply, right? Similarly, same concept for this fixed walls, and front and back, as I said, this should be empty. We don't need to solve in Z direction. And this is another again default command that is used. I'm not aware for now, but you can search online. So this is basically a typical entries in the block mesh dict file, right? Again, another important file in the system is this control dict file, right? So inside this control dict file, we are going to use the application that I was talking about in the earlier session, the solver, ICOFOAM, which is piezo-based algorithm, which is unsteady. It is valid for incompressible kind of flows. Again, start from is the flag. It is start time. So basically what it will do is you have specified the start time. So it will look for the start time entry inside this particular file setup. So inside this start time, it will find another start time over here on the left hand side, right? And on the left hand side, it will look for the scalar value. If you specify 1, if 1 is existing inside that folder, let's say like you are simulating particular flow and it is running for some time and you have stopped the simulation and again you want to reiterate from that particular location only. So whatever time it has stopped, you need to specify that. Or alternatively, what you can do is instead of start time, you specify it as latest time. right? This is another flag that is allowed. So notice that the first word is not capitalized. Latest here L is small, and after that subsequent word which you need to append should be capitalized. This is the standard convention that OpenFOAM follows, or any C++ oriented programming oriented course follows. So instead of start time, you can specify this as latest time. If you have the latest time available in your folder, it will start from there. Otherwise, if you don't have anything, only zero is there, it will pick up the zero and start the simulation, because latest for that particular is zero only, right? End time is again very simple. It will again search at end time, and end time is available over here, whatever value is specified. Let's say if I want to simulate this flow for 100 iterations. So I specify 100 over here and it will keep on iterating, right? And after that, this is delta T. This is an unsteady solver, right? And for DDT schemes, if you discretized it, if you go into the discretization, right? Del U, let's say some del phi by del T. So if you discretize it using finite difference at least, so it is phi n plus 1 minus phi n divided by delta T. So this determines the stability of your code. So this is what we are exactly specifying over here. With 0.005 seconds, the solution must advance, right? Again, write control is time step. Time step is whatever time step we have taken over here, delta T is 0.005. It will start writing in that interval. That is, it will find the right interval as 20, and 20 into 0.005. After that while iterating, if that number achieves, it will see 20 into 0.05 is the interval that has been created. It will start writing. So if you multiply this, it will write in 0.1, 0.2, 0.3. Those kind of folders will be generated, right? Purge write is again another entry. Let's say if you have a lot of data, if you're solving very steady state problem, it at the end of the time, like flow in a pipe, it must develop a parabolic profile. So if you are using unsteady solver, at the end of the time it will be a steady state solver. So what we are trying to do is we will throw away all the initial transients. We don't want the initial transients. So parse write, let's say if I put 10, so it will keep only the latest 10 folders. The rest of the folders, it will keep on removing that. If the solver is running, let's say if you have 10 directories, if I write purge write as, let's say 5, right? So while solver is running, it is now yet it will start writing the next time step, right? It is the new time step it should write. But purge write says it should be 5. Now total we have 5 folders. It will start removing this folder. It will delete that folder, and this would be the next set of 5 folders that it will write. For the next, it will append that list with 1 and remove this. So because we don't need the initial transients, we need to optimize the space for whatever hard disk we have. So we are interested in just keeping the latest 5 time steps. So for that, we need to write parse write as 5, 10, 20, whatever is your requirement. Write format, again, it is very straightforward. You can write that data in ASCII format or binary format. If you write it in binary, you cannot read it, but you will save considerable amount of space in your hard disk. Write precision, again, very straightforward, up to 6 decimal places. Let's say if I have a folder named as 0.0000000. If write precision is 6, it will treat as 0 only. It will keep first 6 significant digit. And after another iteration, it will write 0.00000 0.2, right? Again, since you have given very less number of precision, so again, it will treat this as 0 only. So you need to be very careful how much precision data you want to write. So for this, the best practice would be write 10-digit precisions, right? Write compression, again, while we run the solver, we will see that it will create folders, right? So compression, what it will do is it will pick the folder and zip that. zip that folder into particular 0.gz format. So it will try to compress. It will make a file out of that folder, like we use the WinRAR and WinZip kind of softwares to compress our data. So it will further reduce the space. So it is also advisable. ParaView basically is able to read this compressed data. TechPlot does not read it. So we need to be very careful if you want write compression on or off. Time format is general. There are several entries available. If you general in the sense, there is another time format which is in this manner, 1e minus 6. This is called scientific. So we don't want this kind of format, then you can keep that as general. So instead of 1e minus 6, it will write as 0 point something 1, right? Again, time precision after how many, like in the delta t, if you specify while current number is varying. So current number is basically a number that dictates the stability of the solver. So from current number, it calculates the delta t. And what is the delta t, at what precision you want that delta t, that is being controlled using this time precision, right? And again, another important flag is runtime modifiable is true or false. So let's say your code is running for very long time, and suddenly you start to remember like, okay, now I want to end the code here and now itself. So instead of, let's say your end time is 100 and you are at 52 location, 52 time step or 52 seconds. So if this is true, while the code is running, if you modify it 52 and save that file, it will automatically detect that it is end time is 52, it will immediately stop it, right? If this is false, whatever changes you make inside that, it will not pick up. Before firing the job, whatever data has been set, whatever parameters has been set, it will take that only. You cannot change in between. So sometimes this is useful when you don't want to stop the simulation abruptly. Just want to, again, there is, let's say, just you are nearing particular iteration. If you want to stop at that particular location by saving properly, you keep this as true and change it, save that file, and then you can exit the program without any errors. Another important file that we have is FV schemes. This has been already discussed by sir. In every governing equation is a standard, convection diffusion equation, unsteady convection diffusion equation. So there is unsteady term, as I have already explained. This is Euler time stepping, right? Phi n plus 1 minus phi n divided by delta t. There is Crank-Nicholson. There is backward. Lot of schemes are available. If you just misspell it, let's say it is Euler, and if you put a x over here, save it and run the simulation. So before running the simulation, it will say this is entry is not allowed. These are the list of entries that is allowed over here. So we can play around with that as well. So for initial case setup, it is always advisable to go with very diffusive scheme. Euler is first order. It is Gauss linear. It is at least second order. There is upwind kind of scheme also. There is quick scheme also. So those kind of schemes are already coded. We just need to fetch in over here, use it in our simulation. Sorry. Any questions? Okay. Another is the gradient term that we need to handle in the governing equation, gradient of P. This term appears, right, in the momentum equation. So what scheme it uses is, it uses Gauss linear, which is just central differencing. Another is divergence schemes. Again, it is Gauss linear. Divergence is U dot U, right? This term appears in the convection term in the governing equation. So again, we are using Gauss linear for phi U. Laplacian schemes, we have this term also, del 2 del 2 U by del x square mu times plus del 2 U by del y square and so on, right? There is a Z component. So this is the Laplacian term. And again, you are using central difference with orthogonal corrections. Let's say if your mesh is very skewed, this is the best mesh, right? The face center or face vector joins the center of the two cells. So basically the angle made between the line joining center of two cells and the face vector is 0. This is the best mesh that we can obtain. Let's say if our mesh is something like this, right? At certain turns, we can have a very bad quality of mesh. It is up to us how we generate the mesh. So the center of the two cells is like this, right? But face normal is in this direction. So there is some offset between those two vectors. So this angle theta is what is dictating the non-orthogonality of the mesh. So this kind of uh, Laplacian terms handling in this kind of mesh is quite tricky, because there is a whole set of mathematics associated, which is not feasible to discuss it right now. So it needs a normal vector, and that normal vector should be resolved along this. It is best to resolve the normal vector when diffusion is happening in this direction. Nu f grad u, let's say, into that mathematics appears dot n vector is there. So if you want to calculate this grad u, so you will take this point and this point, divide by the distance between them. But it is again that diffusion, we want it in the n direction, right? If that mesh is highly skewed, the worst possible quality is this 90-degree. So this dot product will give 0. What it essentially will say that there is no diffusion, but physically that is not possible. So what I'm trying to say is if the mesh is very skewed, that diffusion component reduces. So we need to take care of that, and that is being handled using Gauss linear orthogonal scheme, right? And there is other set of interpolation schemes like there are two control volumes. So while calculating the schemes, we need all the quantities at this faces, right? This is control volume center, and this is face center. Because we need to evaluate fluxes crossing through these faces. This is essentially what finite volume does. You have information available only here. Let's say this is west cell, and this is the current cell, P cell. So we have nu W and nu P, right? But we want nu is the viscosity that I was referring to. We need viscosity at this also, at this phase also. So this linear scheme, what it will do is mu W plus mu P divided by 2. We'll do central differencing, right? Or take the average of those two values and then put that on the face, provided that this delta x and this delta x are equal. Otherwise, it will do weighted average of the cells if that is a non-uniform mesh. We don't need SN grad schemes for now, but still it is defined as default as orthogonal. And last, after you convert the after you provide the mesh, use the discretized form of the equations, write for every cell, and you will obtain a big matrix Ax equal to B, and that we need to invert to find. We have the B vector, we have the A vector. Only thing is we don't know the X vector. For U, V, W, P, that is the X vector. So we need to invert that particular matrix X equal to A inverse B, and from that we can find out the solution. So this inversion process, if you have seen or if you have come across the complexity associated with it, if you directly invert it, it may basically be very cost expensive. This is what scaling was all about. If you can handle that inversion process effectively, your solution or your simulation will be very fast. So there are various n number of uh, algorithms available to invert that particular matrix. One of the algorithm is use the Gauss-Seidel approach, line by line Gauss-Seidel approach. So all those things are already present in here. I am, to be honest, I have no clue of all these PCGA and smooth solvers because that is a whole lot of different applied mathematics over here. Only thing is we adopt the standard solvers from the test cases. And again, if you do the spelling mistake over here, it will show up all the list of possible uh, solvers that is available in OpenFOAM. You can try out with different kind of solvers so that your solution converges. So for that, you also need preconditioners. So all those mathematics is not I'm discussing right now. Only one more thing that I want to say is the tolerance. Tolerance is if your tolerance of the if your error accumulation falls below 1e minus 6, then your solution will stop. This is for this is specifying tolerance for P. P final is required when you do the inner correction, outer correction. So that is being handled in the piezo algorithm. So it is saying relative tolerance is 0. We don't worry too much about the P final. Only thing is if you are able to reduce the P residual to 1e minus 6, then we are good enough. For you, it is 1e minus 5, right? But the solver that we use is symmetric Gauss Seidel, and smoother is symmetric Gauss Seidel, and we are using smooth solver for inverting the matrix. And this is basically piezo control loop. So how many characters do you want? Like I said, there are if there is mesh is very non-orthogonal. So you need to emphasize the non-orthogonal characters as 3, 4, or 5. And this is very this is very expensive iteration. So the best practice over here is to make the mesh as orthogonal as possible, right? So only if you make orthogonal, if the orthogonality, that angle that I was talking about, is less than 60 degrees, then mesh can be treated as a good mesh. So then in that case, you can keep this non-orthogonal characters as 0. And proportionally, you can increase if the orthogonality, if somehow you are not able to reduce it, you can increase the non-orthogonal characters, but it does not, will essentially, it will not ensure that convergence of your solution is obtained. So it may give very erroneous results. So this is the contents of the particular case setup. We discussed zero, we discussed constant, we discussed system. So first, we need to convert the mesh that we have already declared in the block mesh dict that I've already explained you. So for converting the block mesh dict, what the first command that I want to do is block mesh. It will essentially look into the block mesh dict file, whatever information it has, it will try to convert into OpenFOAM readable format. So what it has done is it has picked the block mesh dict file. It has picked up number of cells. As I've already said, that is 20 by 20 problems. So it is 400 problems, 400 number of control volumes it has created. N faces, it is number of faces in the shared. If you discretize the control volume, there are certain phases you need to take care. So that phases has been converted out of 1640 cells or 1640 phases. If I make that picture again, okay. So these are phases. First phase, second phase, third phase, fourth phase. There would be 20 phases over here, 20 phases over here. These are all exterior of the domain. And whatever phases we have inside here, which is sharing between these two particular cells, are the internal phases. So that has given the number of counts of external phases and internal phases. So it has created the patch, moving wall, fixed wall, front and back, which we have declared in the block mesh dict file, right? And what we need to do is, after setting the block mesh dict file, we need to fire our code, which is icofoam over here, which is piezo-based algorithm. So if you do ls over here, it has created 10 different folders, right? And it has been written in the intervals of 0.1, 0.2, 0.3, and so on. So since our end time was 1 over here, our code stopped, right? If you have specified 100 over there, it will keep on running till 100 iterations are obtained. So what we are essentially going to do is we need to visualize what we have simulated now. Are you able to follow up to this point, or should I do it again from the start? Go back where? Okay. So this is the complete clean case, right? From here you want that simulation to run, or from the starting, from where, this point onwards? Okay. First, what you need to do is you need to make the mesh from the block mesh dict file. OpenFOAM readable format mesh you have to create. For that, first command that you need to run is block mesh.
Hello? Hello, is everyone able to run? So one thing you have noticed that you are running this in login nodes, right? Everybody is in login nodes. Many of you have already done this, but probably they have run in the login node. So login node is not actually, we are not accessing the HPC. Okay, I know this is a very small case. Okay, it doesn't make any sense of taking any reservation, but still in clusters, you are generally not allowed to run in login nodes. A maximum runtime of what 5 minutes is allowed. In Paramashakti cases, anyone can try, but if you run it for more than 10 minutes, you will get a mail from here, okay, that you are running for more than 10 minutes. So I will be just showing you just to how to get a single core, okay, for for this case, we just need a single core. So in the main NSM KGP folder, all right. Everybody, please do not open, because you might, if everybody opens, there will be an error. So in the NSM KGP folder from where you have copied everything, there is a run underscore reservation.sh file. Okay. So this is basically a script file which is used to get allocation of resources. So here basically what we are saying is, uh, so we have reserved for you 3 CPU nodes. Okay, so basically 120 cores we have reserved for you. So here nodes you can see from the second line. Okay, so if I just explain it, you have a job name written. So it basically says the name of the job. So when you will submit, this is what you will see. So if you don't name it, if you must submit multiple jobs, you will not be able to understand which job is which. So it's good to have a job name. Okay. Next, nodes is basically how many nodes I need. So each node has 40 cores here in Param Shakti. In Param Shiva, maybe 42 or 48, right? In Param Siddhi, it is 256. Okay, so it depends from cluster to cluster. Here is a member CPU. They have it's written 3000 MB. It will be MB, I think, or 3000 MB. You can specify that or not. It depends upon you. Time. So time is, this is 2 days. Sorry, 2 hours. Okay. So max in Param Shakti, the max is 72 hours. So depending upon your how much time it will take, you can change the time. Okay. So those who from KJP, those who are running and not able to get jobs quickly, for them it's a tip. So if you know if your case will run within 2 hours, mention 2 hours in your wall clock time, not 72 hours. Okay. So you will get the job faster then. Next, error file. So if you have any errors, it will be shown in this file. Job dot percentage j. Percentage j is basically the if when you submit a job, you will get a job ID. So percentage j is a job ID. I will show you after this. Output is job dot percentage j dot out is the output file. And for this workshop, we have created a special reservation. So that is named as reservation equal to workshop. So many of your professors might be having reservations for high priority queue. So there you might be using partitions and reservations also to get the jobs faster. Okay, so this is basically how a script works. So if in any Param system, wherever Slurm is used in any Param system, this is the basic structure. Whatever you use a Param system. Now, so you have seen that icofoam is the executable file name, right? So here, uh, if I mean, most of you are familiar with, I think, coding, right? If you when you code, you write to execute a file, a dot out, probably most of you, right? The star dot slash a dot out, most popularly used. So that's an executable file. So when you don't mention your executable file name explicitly, it generally becomes a dot out. So here our executable file is icofoam. So we have mentioned icofoam, and ex is basically a variable here. Okay, instead of mentioning icofoam multiple times, if I write exe is equal to icofoam and then use exe, you can see it at the last line. $exe is basically accessing the exe variable. So I am saying exe is basically icofoam. So I'm just running icofoam. And the next part is basically just writing it to a file. So many of you must know this, that there's ampersand greater than sign. We can write the files to the name which is given after that. So basically what I want to do, I want to execute icofoam. I want to write the contents of that executable in log.icofoam. All right. So this is basically what we are doing. The hash are comment lines, the hash below. So we are commenting all this. Echo is basically meaning that we are printing. So this message will be visible. All right. So let me just show you how it appears. This is very straightforward, actually. Yeah. So it just if you let me show you, it is not that difficult. So the file is runreservation.sh. Okay. Now, if you have to submit it, you have to do sbatch runreservation.sh. So I was mentioning about a job ID. So this is a job ID you get. All right. So you were saying my job ID is about 1420. So if I do SQ here, so SQ is basically showing how many jobs I've submitted and what are the job like what is the name. So so the partition. So here the things to note is my job ID is 142303. So uh, someone else has also submitted because see my job ID was 1420302, but here it is showing 1420303. So someone else has also submitted, and since the job was very less, timing was very less, it actually completed. Okay. So if I so 14203, someone else has also submitted the job, and we are using only CPU nodes. So the nodes here is shown CN001, and time is 7 seconds running. So if I do SQ now, it has stopped because since the runtime is very small, it has stopped. And partition is shared. Basically, shared means CPU cores. So now if you want to run, if you want to have multiple cores, right? If you want to take MPI or multiple nodes, you have to just change this here. Okay. So everybody can try this. So just this was just to show that you can like to get how to get the codes. Those who are in test user one, they can just copy this run reservation to their own folder. Okay. Actually, in every NSM KGP, it is there. So just the way you copied everything, you can copy it there also. The NSM run reservation.sh and just do sbatch, you will be seeing that it is running. Okay. So since we had the job time was very small, you did not get any errors this time. But if you run more than about 5-10 minutes in a login node, there will be error. Okay, because and it will slow down your like access because login node is just for accessing the cluster. Okay, so test users one can actually do this. It is the run reservation is modified in your case. So from NSM KGP, I have shown you this path from NSM KGP cavity RE100. There is a run reservation.sh, and others those who are not comfortable, you can just run it on the login node. There is no issues. He will show a MPI case where he will be using probably 4 cores. So then he will be showing you that. But if you are not comfortable with this, you can just run in the login node and get the results. Right. This is yeah, Ross data is fine. Okay, can you just confirm if you in NSM KGP, anyone from test user 2345, if run not run reservation.sh is there or not? It is there, right? In all the tests. Okay, can you copy that to your folder? Just copy that file to your folder and just make these changes. And if you cannot make these changes, it's okay. Just write comment everything and write ICOFOAM. It will run. As is for commenting. So in NSM KGP, the run reservation.sh is present. Just copy it to your folder. Folder, I mean cavity RE100. Cavity RE100. Okay. Those who are not comfortable, you can just run it in login node. There's no issues. He will be showing probably a MPI case. He will be showing an MPI case later. Okay, he will be not showing MPI case. Okay, tomorrow he will be showing. Copy the file from NSM KGP. Okay, from NSM KGP, just copy the reservation file to your cavity and you can run it. Is anyone able to run using script file? Sure. Okay. Anyone? So test user 1, test user 5, they're able to run. Anyone facing issues with running with script? Has everyone copied the reservation file to their folders? Anyone not copied yet the file? Just and then just change it, change this accordingly. ये टेस्ट So in NSM KGP, the reservation script that will be seeing is not the same as it is shown here. Okay, just make the changes as shown here and then run it. So there will be, so basically I'm mentioning the changes. You will be seeing in the NSM KGP script file that you have copied. You will be having n tasks as 4. So make that n task as 1. Next, you will be seeing that no exe is mentioned. Okay, just write exe equal to icofoam, and in the file, I think interfoam is written. Right, so just change interfoam to icofoam and comment the echo decompose, and the next line delete that. And in the last line, comment MPI run. So please open the, if you have copied your script file to your folder, everybody please open the script file. I'm just mentioning the changes, okay? So first change is end task is 4 in your case, and make end task 1. Just check the script file. If you have copied it from the NSM KGP, end task is 4 there. Just make end task is 1. Then there is no ex equal to icofoam written. Just write ex equal to icofoam. Okay. Then comment the comment the echo decompose thing, and the one below that, both the lines. Comment the MPI run line. Comment you have to do by hash. Just write hash in front. After doing this, after you have done this, go back, quit, and do sbatch, then run reservation.sh. Sbatch, then the script file name. It's the file, right? So just you can do CPR also. Okay, I'm just showing the. It is CP. It is CP, right? Then the path NSM, probably NSM KGP, right? That thing. Then write run reservation that file name. Okay. Then if you are in your own folder, then just put a dot if you're in your own folder. If you're not in your own folder, give the full path of your folder. And there will be a space between. So I'm repeating again. So these are the changes. Anyone who is able to run it using script other than both of them? Okay, so one more thing, just comment this since we have comment this also because you are directly copying it in your folder, so don't need to do any CD or anything. Okay, any doubts? Anyone who's not able to block mesh? Acha, right. Microphone. Okay.
I hope everybody is able to now at least run the code. Or shall I wait for some more time or shall I move forward?
Should I? Okay, just do you need some more time to run this, or do you want to go to the next case?
No,
How many of you want to
I'm
have
not
more?
going to next case. I will download this and explain everything on peer review, what we have simulated. Okay.
Huh?
PPT is there. PPT is there, but in day 2.
Recording lecture will be shared. If those who are having issues with running the script, you can look into it later. Right, okay.
Without what? Okay, moving further. I hope.
Okay, let's go to the next case. If anyone wants to later look into this, we will take some time.
Okay, so if you have, there are two methods or various methods to download the case files already present that we have already simulated. The first method is using MovaXterm. If how many of you are using MovaXterm?
Okay. Okay. How many of you are using terminal? Please raise your hands. How many of you are using terminal? Very few. How many are using MovaX? What are the rest of you using? Huh? Oh, Windows. Okay. Yeah. Okay. How many are using Windows? Most of you are using Windows, right? Okay. Windows people have WinSCP. Download WinSCP. Okay. And Windows people download WinSCP. Easier way. Linux guys, Mac guys.
Okay.
Okay. For this Linux, Mac, and terminal ones. Okay. SCP. So basically, we need the files from Param Shakti to our current local machine to get the simulations, right? So Windows, you can have Windows. Those who have, you can download WinSCP. Very easy way to transfer files. Those who have Mobax, we will show you. It is on the left for Mobax. It is on the left hand side. Data file transfer. Other than that, those who are using terminal, those who are having Mac, Linux, we will be showing first showing the using command how you can transfer your files. Okay. So first is okay. Please pay attention, guys. You have to visualize the results, right? How many of you have downloaded ParaView? How many of you have not downloaded ParaView? As everybody has downloaded ParaView. Okay, good. So okay, so basically first, as a ParaView.
Test case.
Yeah. Okay. So okay, so everybody please go to your. So this is for terminal, Mac, and Linux. Please go to your this command prompt. Okay, and we'll be seeing something like user something. Okay, do ls. Okay, ls is not a pw is also I think not. Acha. Dir will be showing you where you are. Okay, so if you want to copy it, so I want to copy everything here in uh, say PC. I want to copy everything in my D drive. Okay. So just do cd-d. Sorry. Okay, let's maybe something is wrong. So let's try with the current whatever folder you have. So first do scp, then go to the file path that you have. All right. So say you are in cavity RE100. Everybody is in cavity RE100. Do pwd. You will be getting the file path. Just copy this. Just copy this. Now I want to basically have the files from Param Shakti to your current current system. So I am in test user 1. Okay, so if you're in test user 2, 3, 4, 5, change accordingly. @ Param Shakti. Okay, write this thing. Then copy the path. Okay, so you can see the files are copying. I will repeat the process. Just okay. Just to show the files are copied, I am in C users in instructor. Okay, so if I go to PC C users instructor, okay, I copied. Okay. So this, so you can see these all files are I copied. I should have copied the folder actually. Hmm. Okay, you can see you have cavity RE100 here, right? Which has everything. So this is basically what was in Param Shakti. We have it in a local system. Now you can use ParaView. All right, now let me show it again. So you have you have to do SCP minus R is for recursive to copy folders, complete folders. So one way is, so you can you copy both ways, but since knowing the IP configuration and your host username of your current your local is not that like easy. So what we do, we take the path from the Param Shakti. Okay, so we know the Param Shakti path. We copy that path. So it is test user. You should have to write test user 1, 2, 3, whatever that is, @ paramshakti.itkgp.ac.in colon. Then give the full path. Path you will get from PWD. Okay, wherever you are in Param Shakti, do PWD, you will get the path. Copy that path. If you want to, I want to copy the full cavity RE100 folder into my system. So keep that path, and that dot basically, see, then there is a dot at the end, full stop or dot. So that basically means I want to copy everything in my current folder. There must be a gap between from the place from the source to the destination. So my destination is basically the dot, which is the current directory. Okay, so there should be a space between the current source and the destination. Basically, the where you are currently located, that is dot. You can put the path here, but I am there is something, I'm doing something wrong, so I'm not able to change the path. But yeah, so just copy it in your system, and after you have copied it, you can go to the you have GUI interface here. You can go and then get this. So it will be varying for every one of you, whatever is your current folder. Okay, just go and check it. The file should be there. Anyone is able to do this? Copying the files. Okay, for this is for Linux, Mac, and terminal. For WinSCP, guys, you have to show for WinSCP. Achha. Okay, for Mobax, I'm showing. For Mobax, you have basically SCP. This is GUI based, like the same thing, but we have GUI based. So you have SCP here. Go to follow terminal folder. Okay, no need follow terminal folder. No need of going to terminal folder. Just go to scratch. Where is the? Okay, so okay, so you can see it is taking a bit of lagging because many are using it. So if you are on the right hand side, if you are in your directory which you from where you want to copy, on the left hand side, just do follow terminal folder and click refresh. You will be in the place where you want to copy. So you can see I'm actually inside cavity RE100. So it is showing everything from cavity RE100. I want to go back a bit. So if I do cd dot dot, or you can go back manually also. Okay, so you can go back manually and just copy this, click all this. You can see. So I got back. So click this and then do download selected files. Then give the location of where you want to download. Okay. So if I want to download in so you can see downloading cavity RE100. So Mobax will be a bit slow. I'm showing for WinSCP also. And sometimes Mobax, it shows it is copying, but it doesn't copy also. Okay. Okay, for WinSCP guys, host name is same Param Shakti. For people outside the KGP campus, it will be 4422. For inside 22. Username is test user 12345. Same as password. So you can see I have got here on the right hand side is basically Param Shakti. Left hand side is location of your current of your system. Okay. So here I am in D folder. So if I want to go to Chitrak, oh, the Chitrak is not. Let me go to. So just show here. Here the open directory bookmark option is there. Go to that. Now you want to go to scratch basically where you were doing in Param Shakti, the same location. Go to scratch. You will be seeing all your folders there. If I'm going to Anurag 14, I want OpenFOAM day one, incompressible, cavity RE100. Okay. So I want to copy it here. Just drag and drop. Okay. So the first time you have to give a captcha, but for the next time you don't have to give. So you can see on the left hand side, cavity RE100 is present. So WinSCP is way faster than Mobax, actually. So for Windows, those who have WinSCP, they can this to copy the files, and those who have a terminal, they can use SCP to copy the files. Okay. Now Anurag will show how to use it in ParaView. Everyone has copied the files, right? Anyone still is unable to copy the files?
Okay, so one more thing that you need to do for visualizing the data is you need a file inside cavity RE100. You should have downloaded that earlier. Anyways, I'm going to show you. Now you know a bit of how to download that. You want to create one file which is named as para.foam, right? This para.foam, this para name can be anything XYZ ABC, but the extension must be .foam. So touch is basically what it is doing is it is just creating a file and then exiting it. You are not editing anything inside that. So if you execute this command and do ls, you can see this para.foam has been created, right? And if you refresh it over here, this is what has this is what I have created. So just click on download, and it was cavity RE100. I am just downloading at the particular location. For again, if you are using terminal or Mac or Linux, so again you have to follow that process of SCP -R and the process that I've already told, right? So after doing that process, this para.foam must appear in your particular case directory. This is essential to open the case setup of the OpenFOAM file. So now open ParaView. Right, and then click over here to open. This is all GUI based. I hope you all know how to open and close a file, export a file. So navigate to that particular location. It was in desktop. Oh, sorry. It was in instructor, cavity RE100. Please navigate to your particular download location where you have already downloaded. And cavity RE100, here this para.foam must appear, right? Just click OK and hit apply. So this is what you have already solved for now. So this is the contour of pressure. This is contour of velocity, right? Lid is moving, so it is having highest velocity at the top, and here the flow is recirculating. We want to create streamlines. This is stream tracer. Click over that and just hit apply. And reduce the resolution so that you can see it better. There are a lot of options are available, right? So this is what a typical streamline looks inside the cavity. Then another thing that you can do is what I already told you earlier. I want to plot a data over this line passing through this geometry center of the cavity. So there is another filter. You search over here, type plot. And I'm interested in this filter, plot over line, right? So after you hit enter, what it is doing is it is passing through this corner and it is terminating at this particular corner. But I want this line to be passing through the geometric center that should be vertical. So this is basically, if you see the XYZ Cartesian coordinate system over here, so it should be along the Y. So simply hit Y axis over here, right? So now it is passing through this particular location and the start point is this particular location. And line is passing through this geometric center of the cavity, and then hit apply. So this is what we are not looking for. This is basically plotting the data according to the arc length. So what it is doing is it is discretizing this line into several points and using this as the x-axis, and whatever properties that you have already simulated. Let's say U magnitude, Ux, Uy, Uz, pressure is what it is simulating. So U magnitude is vector. So it has three components, Ux, Uy, and Uz. So what GI has provided is variation of Ux along this line. So what I want to do is I don't want to use the arc length, but rather I would like to use the Y points, that is vertical lines discretization. And I don't want U magnitude, right? I just want Ux over here. Select Ux. So this is what GI is provided. Along this, Y is varying, and along this, X is varying, U is varying. Alternatively, in most of the papers, people plot it like this. They make this as x-axis as U and x-axis as U and y-axis as points Y. So along this, what I have done is I've just flipped the graph. So y-axis now represents the y-axis of this lid-driven cavity. This is the y-axis. This is what it is varying between 0 to 0.1. This is what we have discretized the computational domain, right? And this is the variation of U along this x-axis. Now what I want to do is I want to save this file. I want to save this plot. Go inside file, write save data, and create one dummy folder name by clicking right click and create new folder. Let's say this is test. Go inside test and write the file name. And that file should be comma or tab delimited. This will write in CSV.file format. So this is again data. You can put it any name. And this should be all default. You can increase the precision after decimal points and then hit apply. So what it will do is it has created, I have created the name as the test over here. Okay. From where? From here. Okay. So ensure that while saving the data, you can select either of these two screens. If you can see a blue border is highlighting that. So select this screen, this line plot. Okay. Go to file and then save data and create one folder and save accordingly. I hope okay, most of you have not not able to create this particular para.form file. So this is the command to do that. Right touch para.form and hit enter. You do ls, it will create para.form file and you need to download in your particular case directory. So anyways, what I was saying is you have already made a folder named as test. You have the data available. So it must look something like this. You have view, that is x component of the velocity, y component, z component pressure. Don't worry about this. Arc length, this is what I have already talked about. This is x coordinate, y coordinate, and z coordinate, right? So I want the variation here, what he has provided is he has provided a non-dimensional data of u, something like this. So this axis is varying between 0 to 1. That is u is non-dimensionalized with respect to the lid velocity, u lid. Okay. So u we have already taken as 1 and u lid is already 1. Sorry, u is what we have obtained and u lid is already 1 meter per second. So we don't need to normalize the this x-axis. X-axis is u, but y-axis, if you notice, our data is varying between 0 to 0.1. But Gia has provided the non-dimensional in the non-dimensional format. So what we need to do is we need to divide this x-axis by 0.1. This y-axis or 0.0, 0.1, 0.1 data is the y-coordinate. And this is varying for now in the dimensional case as 0 to 0.1. We want to make it as variation between 0 to 1. So what I'm suggesting is you can use any manipulation software, let's say Excel. You can manipulate whole column, divide the whole column by 0.1 and obtain one raw data format like this in the CSV format. Right, this is what I have already provided. Right. So the first column is the U and this column is what I have calculated. Okay, I hope I am able to explain what I want to do. You just need to normalize that axis. So basically, this is here U100 and this is CFD what we have obtained. We need to plot on top of this each other to know whether our solution is correct or not. So again, I'll use ParaView. and close this, right? And go into line chart view. So this is where we want to plot our data. Again, navigate to that cavity RE100. Right. So what we have here is we want to load the data of 100, use the CSV reader, and then click enter, then apply. Close this, it is not required. Just there is one I option over here. Click on the I, right? Now we want to set the axis. Don't use the index. Just X axis must be U velocity. So I'm using U, and don't plot everything. We want the Y axis to be Y. This is what we have got, right? This is the data provided by GIA, and this is at discrete locations. So we don't want to plot this with line. We want to plot this with circles. There are small circles appearing. Want to increase the size. Let's say it is 10. This is what GIA is provided. Now again, open that particular CFD file that we have already made. Open it using the same CSV reader. Again, click apply. Close this, you don't need this. Again, click the I view. Don't set the index. X-axis must be U, and this should be Y-axis. And change the color. This is CFD. This is GIA's result. So technically, our graph will look something like this. So we have simulated RE100 case successfully. So the next exercise that I would recommend you to do is simulate the RE400 case, set the viscosity parameter, U parameter, do all the exercise, then at least you will get an idea how validation and all those things are done. Okay. So up till now, you have plotted the data over line. You have obtained this curve, right? So ensure that this line chart view is selected. After selecting this, click on File and click on Save Data, right? And create one arbitrary folder. Arbitrary in the sense data and so on, and then save inside that. And ensure that this is comma tab delimited. Sorry. Okay. So one of the doubt was how to change the axis. So ensure that this box is not tick marked. Otherwise, there is no option to change that. So untick this, and X array is the X axis. You set whatever X axis you want. You want Y or U, it's up to you. If there are many other variables, you can choose other variables as well, right? So for X array, you set U, and for Y axis, don't plot all the data. You just plot the Y data. Since this is an open source, so basically it is little bit difficult to plot all the data. I preferably use TechPlot MATLAB for plotting all my data. It is much more convenient than this. Okay. You don't have to basically manually create an Excel file, divide that by 0.1. You can do, once you load the data, you can do everything inside that software. So I would suggest to learn TechPlot or MATLAB or Python. Even GNU plot is also a good option for open source plotting software. I think I will be not able to cover the oscillating cylinder case since it is already time up. But if you want, if you are patient enough, then I can little bit of discuss and so that case can be skipped probably. OpenFOAM. People are transferring that, but otherwise people generally use commercial softwares only. Yeah. So because it is bit more easier, there is a GUI based. You just need to click and set up your case. This is much more research oriented, but people are shifting to OpenFOAM. Yeah. There are no further questions, then let us wrap it up and we shall meet tomorrow.
Online participants can leave the meeting. We are wrapping up for today.